Welcome to today's webinar, USB Type-C and Power Delivery Technology and Testing. I'm Mike Micheletti, and I'm a product manager here for the USB testers at Teledyne LaCroix. And earlier this year, we celebrated our 20th anniversary of working in the USB ecosystem, going back to 1995 when we were CATC. We build analyzers for a lot of different serial interfaces now, but we're in sort of a unique position when it comes to new technologies. We can actually predict which emerging standards will get adopted based on the analyzer sales rate. And all I can say is that in the first quarter of shipments, we've broken our own sales record with the new Mercury T2C. That's our low-cost Type-C analyzer. And this is in terms of units. So that tells us two things, that Type-C is ramping fast and that it's a little more complicated than people thought. They've added a lot of capabilities with Type-C, really expanded the number of things you can do over a USB cable. We're definitely seeing more activity, more innovation, really more excitement around USB. There's a lot to cover in a short amount of time here, so we're going to dive right in. Most of this material is specific to the protocol layers, getting the link configured. We'll move quickly through cable detection, spend a few minutes on message types before looking at real traffic with actual devices. I'll bring up some interesting test issues. I'm sure there'll be a lot of questions, so please type in any questions using the question box. We'll address everything we can at the end of the webinar. And definitely, I'll send out the slides to everyone later today, so stick with us. At the 30-minute mark, we'll pick one lucky winner for our Mercury Type-C analyzer giveaway. This is the fully loaded advanced model, so hey, the odds are good. And I'll definitely announce the winner at the end of the webinar. If you're on this call, you're probably already familiar with USB Type-C features. The goal was to create a smaller, thinner, more robust alternative to the existing USB connectors. The design was really modeled on the Apple Lightning connector. The reversible plug orientation, where you insert the plug either upside up or upside down, is, well, it's overdue, because what's happened is the platforms are getting smaller and people's eyes are getting older. And it really does get harder to see the right orientation of the plug. So I'm sure this will be popular. And we're surprised by how many vendors have jumped on the alternate mode stuff. We originally thought this would be kind of a niche, but the majority of chipsets at the last Plug Fest have alt mode support. So, well, the USB IF, that is very bullish on Type-C, and they're claiming the fastest transition since USB 2.0 was launched. Power delivery and the Type-C connector have really become linked together, but they weren't initially. The higher voltages in PD were supposed to work over legacy USB connectors using FSK signaling. But interest in FSK has completely disappeared. There's really no activity. Virtually everyone that's implementing PD has moved to Type-C. So the applications are the same, only now it's over a Type-C cable. Obviously, they're targeting very thin platforms with Type-C, your notebooks, your tablets, your smartphones. And we continue to hear that reducing e-waste is one of the driving forces with PD. The mobile market in particular wants a universal charging cable. There's also a lot of interest in video over Type-C. There are alt mode adapters on the market now that will mux HDMI or DisplayPort over Type-C. There's also audio accessories, other applications in the works. There's a lot going on. So the material I'll cover comes from two specs, the Power Delivery 2.0 and the Type-C version 1.1 spec. Anytime you have two complementary specs, the technology can be harder to understand. It's easy to miss things if you have to refer back to two documents. And the Power Delivery spec addresses all the elements of the logical PD protocol, like discovery, negotiation, role swaps. The commands for alternate modes are also defined here. But you'll also need to look at the Type C spec, where they have a section called Functional Extensions. All the logical state machines for alternate modes are in here. But mainly you'll find the electrical, mechanical, the physical layer requirements in the Type C spec. It's too bad there's no plan to merge these two specs, because there's several areas that are still a source of confusion for a lot of developers. Any discussion about power delivery really has to start with the pinout of the Type C receptacle, because it's such a huge part of understanding how the technology works. To make the cable flippable on the new Type C receptacle, they're basically creating a mirror image of the pins in sort of a top and bottom row alignment. If you compare that with legacy USB 3.0, the old pins map to the new pins on this upper row labeled A, and then there's a redundant set of pins on the bottom row that basically won't get used for USB. So if you were to flip the cable, you would still connect to a second redundant set of pins on the bottom row in the receptacle. Apologies if you didn't see that cool animation, but I'm trying to show that you're basically making the same connections even though it's a different physical pin. So the cable plug is flippable, but all the intelligence is really in the receptacle side. So we need to look at that, but before we do, the other key feature is that the entire cable is reversible. Either side can be attached to the host because the plugs are identical, right? But we still need to maintain the logical host-to-device relationship. So when you're connecting a Type-C cable to a receptacle, which row of the pins am I going to use? Okay, that's the first order of business with Type-C. And then identifying the host-to-device relationship is the next critical step. Both are accomplished over the configuration channel, or CC. It's considered a sideband signal to the logical USB link, but it's used to orient the cable and set up the initial data roles. And then even after that, it's used to do all the negotiation for power delivery states. So, I mean, it controls the alternate modes. It's a major component of Type-C. This image maps out all the roles of all the pins in the receptacle. Okay, as I said, there are basically duplicates for every line. If you're familiar with USB 3, you'll see that there are two sets of super speed pairs. Only one set is actually getting used by USB. Same for D+, D-. Only one of these pairs will connect. There are two VBus pins in each orientation. And SBU stands for sideband use. Okay, not used by USB at all. Both of these pins can be configured for alternate protocols. You know, currently, for example, they're used as the auxiliary channel in DisplayPort. It'll also potentially be used for delivering audio over Type-C. But these are, of course, in the cable in both orientations as well. And then the CC line is also duplicated. Okay, so think of this view as though you were looking inside the cable plug and the receptacle housing itself. The upper one is the cable, okay? These pinouts look similar, but there's one huge difference that's really important to understanding this technology. Only the receptacle side has the fully redundant set of pins. The cable is not symmetrical like the receptacle. On the upper image, the CC line is always on A5, and if it's an eMark cable, then VCON is always on B5. There's only one D+, D-, one super speed pair. The extra pins we see here in the cable plug are there exclusively for alt modes. So the cable can come in on either orientation, facing up or facing down, and it will always use the same pins for USB. It's the receptacle's job to adjust the pinout to match the cable. Okay, before we look at that, we need to understand marked and unmarked cables. most of what's on the market today is unmarked. They have no active components, but the marked cables are coming, and these will have a chip embedded in the CC line. So the DFP can actually ping the cable, and the cable will answer back with his capabilities. He'll report whether he can handle the higher voltages. He'll report if he's configurable for alt mode. One of the main motivations here is that a type C source cannot supply more than 3 amps of current unless it's connected using a marked cable. So it's a safety thing. The cheaper unmarked cables are going to be limited to 3 amps. Still, that's higher than legacy USB. Also, with type C, there's a provision for active cables where they're putting repeaters in the cable. In some cases, these components may need to be configured using cable messages. This will also be done over the CC line with commands that are targeted specifically for the cable. We'll look at this in a second, but the main takeaway here is that the type C cables are going to be smarter, and they'll definitely require more testing. Okay, another change. VBus is still used for powering or charging devices, except now there's an option to source higher voltages, up to 20 volts. Now VCON is used solely to power the E-marked cables. Well, also there will be something called a VCON powered accessory, but primarily it's used to power active components embedded in the cable. And that's supposed to happen before anything else on the link. So when the initial source sees an E-marked cable, he's supposed to drive 5 volts over VCON. The cable will only draw 200 milliamps. So it's a small amount of power, but it's critical to the operation of these marked cables. PD does allow swapping source and sink for VBus. There's also a way to swap the VCON source, and when devices do a VBus swap, they'll typically also do a VCON swap. But we'll take a look at that. Okay, I'll give you a high-level summary of the configuration process, and then we'll come back and look at each step in more detail. It's required that the initial source come up in USB safe mode. The CC lines are used to determine the cable orientation. Then VCON is supplied to power any E-marked cables. So VCON first, then the default VBus voltage gets turned on second, by the source that is. Now as long as it's a USB Type-C and it supports PD, you're going to see CC messages that will be used to interrogate the cable. Then there's a two-way negotiation of the power level. After an explicit contract is established, the default data roll device sends discover commands to the port partner to determine if he wants to enter any alternate modes. DisplayPort over C is the most common thing we've seen here. Once there's an established power contract, the DFP sends other vendor-defined messages to configure these alternate modes. Again, if there's no alt mode support, it goes to standard USB signaling. Again, we'll look at this in more detail here in a second. So how does this cable detection work? Starting with the simplest case, a provider only connecting to a consumer. The left side here is the provider or source, and the right is the consumer or sink. And I'm hiding all the other connections in this picture just for simplicity. So both receptacles are powered and monitoring the CC1 and the CC2 lines continuously. Once the cable is connected, they look at resistance levels on the CC pins. The source attaches a couple of pull-up resistors known as RP, and the sink shows a pull-down resistor or RD. So this really on his side. So he takes both CC pins to ground. They only see this termination on the one CC line that's connected, right? So they know this is the line they'll use for PD communications. So now they have to route the other signals I'm not showing accordingly. You flip the cable over, and they'll see the same termination, RP and RD, only this time on the CC2 line. So they need to use the lower pins in the receptacle, in this case, for the logical USB connections. If there's a twist in the cable, it's fine, because each receptacle needs to be smart enough to figure out which pins to use based on the resistance he's sensing on the CC line. So the receptacle will route or mux the other signals to the right pins. Okay, now we're looking at the same setup, simple provider and consumer, except now we have an E-marked cable. So it has the chip inside the cable. And these components need a small amount of power. So this is where the unused CC pin in the receptacle can now be used to source VCON to the cable. Okay, so both link partners are monitoring the CC lines for RP and RD. So the DFP here is pulling up on both pins. He again senses the pull down resistance at the far end. These E-marked cables present a load on the line known as RA. So the receptacle can sense another voltage divider right here. So he knows there's a cable electronics out there that needs VCON. Only after the two sides determine which line will be used as the CC channel, the DFP then applies power to VCON. After waiting, a required timing interval, it can now communicate with the cable itself. Flip the cable over, and the receptacles will still see RP and RD, but it's on their CC2 line this time. So CC1 now becomes VCON, right? It's possible the cable may need VCON at both ends if it has redrivers or active components in the plug. So it's up to the cable to propagate power to the far end plug if needed. But in all cases, VCON is not passed through. It's terminated in the electronics of the plug. So that connection doesn't go all the way through in the cable. Now, the PD spec uses the term DRP to define a dual role port. This means it can act as a source or sink for power. It has nothing to do with being a host or device. Only the power role is affected by a dual role port. Back in the original OTG spec, DRP meant something else. It meant swapping the host and device roles. Not anymore. This does introduce some additional complexity because now you have to decide who is going to be the default source and the default sink at power up. So a DRP, by rule, is supposed to switch between showing RP and RD every 75 milliseconds until he sees the opposite on the other side. This is what it looks like on the analyzer. So we can record this. The DRP is toggling between source and sink voltages. And then the cable comes in, connecting the far end. And he finally sees the pull down. The analyzer shows it as sink attached to the left port. So right there, the source knows he's attached to a sink. You can only have one source and one sink, right? So they can swap later, and we'll look at that. But this is what you see when you've got an established contract or an established connection. So this is the more complex case where you have two DRPs. So both can act as source or sink, but you have to figure out which is which. They can't both come up as a source. And DRPs will be common, actually. Laptops, tablets, basically any battery-powered device with host functionality will have to operate as a DRP. So here is where both sides are toggling between RP and RD every 75 milliseconds. It's effectively a switch within these receptacles going from pull up to pull down, pull up, pull down. At some point, they both see RP or RD on the CC line. The CC pin that's at the higher voltage will indicate which one should be used. Here I'm only showing a single CC wire with only one of the four possible orientations. The other CC becomes VCON if needed, and the DFP should always be the initial source for VBus. So the sensing on the CC pins is what tells the device how the cable is oriented. Then they came up with something else clever. Since they're monitoring the CC line anyway, let's use the pull-up voltage levels on CC to indicate the default VBus current. So this is what the source would provide initially. You know, in legacy USB, there's always been a default voltage for VBus, 500 milliamps for USB 2. That was bumped to 900 milliamps for USB 3. Type C devices can now source up to 3 amps by default. So, for example, as a source, an RP, right after power on, he'll present RP voltages that will advertise his default power. If the source shows 22K at 5 volts, that would indicate he could provide 1.5 amps. If he was capable of providing the 3 amps, he would alter his resistance values to 10K at 5 volts. That means he can provide the full 3 amps over VBus, provided it's a Type-C cable. I mean, he needs to see CRD terminations from the sink to know it's a Type-C cable. So that's twice the current available in the BC 1.2 spec. And this is still completely independent of PD. So you can create a low-cost Type-C device that doesn't even use power delivery, but can still charge at 3 amps. So that's a nice enhancement. So I mentioned that PD and Type-C have a provision to swap both data rolls and power rolls. Again, there's a lot of confusion around this term DRP, which used to refer to data swapping in the OTG world. But, you know, this basically replaces, OTG is dead, right? OTG is gone. It went away, I guess. But in the PD world, DRP only refers to power roll swapping. So a DRP can say, I'm getting low on battery, you be the source. Now, data roll swapping, on the other hand, provides a mechanism for a device to switch to the host role in USB. Maybe a printer wants to send commands to a camera, for example. So Type-C effectively replaces OTG with a sideband mechanism for doing the OTG swap, for negotiating the data role swap portion. Because that's what they need to do. Who's the master, who's the slave? Okay, I'll move quickly through the message types so we can look at some actual captures. So the CC pin allows us to detect the cable orientation. After that, CC becomes the main channel for negotiating and configuring all this added functionality, including power contracts, the alt mode stuff. Both link partners will send and receive packets over the CC line. There are 13 control messages and 5 data messages. The data messages contain some kind of payload. They move in both directions, and there are actually a few messages that can be sent asynchronously by the source, the sink, and even the cable itself. The CC channel is considered multi-drop, which means a DFP can target messages to the link partner at the far end or to each end of the cable. They just use a slightly different frame delimiter to address each part of the link. Most of the frames targeted at the UFP, the device, or the DFP for that matter, they use the SOP framing. Using SOP prime or SOP double prime allows the host to talk to the cable. You'll only see this type of SOP prime traffic if you're connecting to an E-marked cable. Okay, this is pretty simple. The start of packet ordered set is the first bits after a preamble. This is your SOP delimiter. It has a slightly different encoding when targeting an E-marked cable. Most of your SOP traffic, as I said, will have the sync 1112 encoding targeted at the far end, but the SOP prime and the SOP double prime, again, are only going to be used when talking directly to the cable. We'll look at an example next, but there's also some other special framing for hard reset and cable resets. Really all participants in the link only need to receive 3 out of the 4 bits to recognize a valid SOP. So there's error tolerance built in. Cable messages are pretty simple. Typically, you will see these during the initial power on. This is a real capture of the actual cable messages with our Voyager analyzer. The link comes up. We see VBus getting applied. Remember that this is an E-marked cable, so VCON has to be applied first. The analyzer doesn't see VCON because, remember, it's not passed all the way through the cable. We do see VBus going on, though, so you see that at the top of the screen. The source sends the discover identity command, and the response coming back, we see it's a passive cable, so no signal conditioners. The superspeed pins cannot be reconfigured on this cable, so it may not support some of the alternate modes completely. It's a Gen 2 capable cable, and it's limited to 3 amps. So this info gets propagated up where the device policy manager, really software, can use it to configure the link. Okay, I mentioned control and data messages. This is the basic format. Both have a 16-bit header and the same basic format, really. All the fields are shown here. The main distinction is that the control messages have no payload or data objects. Bits 12 through 14, shown here, are used to indicate how many data objects are appended to the message. If that field is 0, it's a control message. If it's greater than 0, it's a data message. So the message type is inferred by the value of this specific field. This lists all the different control message types that are defined in Power Delivery 2.0. This shows the actual bits you would see in the type field. Again, it's only a 4-bit field. Control messages are sent by both sides and are used to negotiate power contracts and role swaps. This is really the nuts and bolts of Power Delivery Protocol. And we'll look at most of these in more detail in a second. The other major component are data messages. By definition, a data message has at least one data object. These are transmitted immediately after the header. Each data object is 32 bits in length. Currently, there are only 4 types of data messages defined. Supposedly, there may be some additional data messages coming in the next revision of the Power Delivery spec, but this is what we have today. There's a few situations, like a device making a power request or reporting its capabilities, where basically he just needs to embed additional information in the message. So that's where these data messages get used. And we'll look at that in a second as well. Okay, both PD link partners are supposed to identify their power role within the header. This field, I don't think it gets used much by the protocol because upper layers are already keeping track of the power role. But it becomes real important when you start looking at analyzer traces. Once devices start doing role swaps, it gets really confusing. So we do show this in the packet header. We abbreviate power role as PR. And you'll use this constantly to keep track of the source and the sink. Another important field, the message ID field, 3 bits in length with a value of 0 to 7. It increments with each sequential message. It's used almost like a tag in SCSI, where it allows a responder to tie an acknowledgement back to a specific command. every PD message needs a good CRC response from the far end. Okay, and that good CRC needs to have the same message ID as the command that it's acknowledging. So it's a simple error recovery mechanism. If you send a message and you don't get a matching good CRC within 195 microseconds, you're supposed to resend the message with the same message ID. Just repeat it. Okay? Assuming the first one was lost, or there can be collisions which can affect those CRCs. Both sides need to keep track of that message ID. That's the key, because it tells you if you missed a packet. Okay, so pulling it all together. This is a high-level look at the Google ChromeBook initialization. This single image represents the entire power-on sequence after it's connected to the Type-C power supply that comes with it. Okay, so this is, it's an interesting case because it's one of the first PD products in the market. So, well, what we're looking at anyway is not confidential. These are production devices, and we're capturing between the laptop and on the left, and the power brick is on the right port of the Voyager in this example. At the top, we see the CC detection of the PD source. And as we saw earlier, the analyzer can capture these state changes on the CC line. They're labeled CC event. And if we unstack these, we'd see the left port is flipping between RP and RD terminations approximately every 75 milliseconds. That's the behavior we expect with a DRP. And virtually all laptops will be DRPs because they need to source current for charging and also supply VBus for bus power devices. So they will almost entirely, exclusively come configured as DRPs. Now the power brick is connected, okay? It's showing RP, so it comes up as the source. And the ChromeBook flips to showing RD and comes up as the default sync. The analyzer can also detect the pull-up voltages on the CC, so from the source, it knows the default voltage here is 3 amps, and it specifies that as well in the capture. Okay, if we were using an E-marked cable, we'd see cable messages next. But the power brick uses an unmarked cable, so it goes right into negotiating an explicit power contract. Our software now groups all the messages that are part of a transfer into a single event. And again, so what we're looking at here is a complete consolidated view of the power delivery negotiation and configuration process. Okay, so if you were to expand these transactions that are part of this power negotiation, you'll see basically all the messages underneath. It starts with the source advertising its capabilities. The far end makes a request. The source needs to accept the request and then send a PS ready. Looking a little more closely, we see source capability message, again, coming from the brick. This is the source advertising how much power he can provide. We see object count of 3, so 3 PDOs to choose from. A power brick will typically just report a fixed power supply, right? Battery powered devices should advertise a battery object, but unlikely to see that from a power brick. Also note that power bricks are generally not dual role. Okay, you will never ask to become a power sink and pull current from the other side, right? He is a brick plugged into the wall. So When the Chromebook determines it wants something being offered, it asks for it with a request. He uses the object position to make that choice. By listing the object position 1 in his request here, that means he wants whatever was advertised in position 1. The source can optionally accept the request. He can also issue, reject, or wait if he's not prepared to support the request right now. After accept, the source sends PS ready once his VBus is activated and he's ready with the requested voltage. It's not an explicit contract until the PS ready is acknowledged with a good CRC, which we see at the bottom of this screen. Okay, back to our 10,000-foot view. After power negotiation, the source sends a sync, actually a get sync capabilities. And he's sending that to the side that came up as a sync, right? This lets him find out what power levels the Chromebook can operate at. So this is the brick sending a message back to the laptop. If you expand that get sync capabilities, it's going to look similar to the source capabilities, only it's coming from the sync. There are 3 32-bit PDOs coming from the Chromebook. There's a fixed and a battery PDO. There's also a variable PDO. The source basically uses this information to set policies at the higher layers. Okay, so next we see the sync requesting a data role swap. Expanding this, we can see the messages that are part of a data role swap. So it's initiated with a control message. Here it's sent from the sync. Okay, the source needs to good CRC it and then also send a explicit accept. So why does the Chromebook do a data role swap? Recall that by rule, the source is supposed to come up as a DFP or host by default. But that's the power brick. So, I mean, it's a wall wart. It's not really a DFP. It doesn't have any real host functionality. So this is one of the quirks of the power delivery spec. This laptop is coming up as a device every time it's connected to its own power supply. So it can't even send the first command on this port until it switches to the host role. Then it needs to interrogate the brick to see if it even supports USB. So now the Chromebook is the DFP. And I think that he's the rightful host, and he can query the power brick to see if it has any alternate modes, whether it supports USB even. And of course, most power bricks don't. So this is where the vendor-defined messages are used. We don't have too much time to get into VDMs and the alternate mode stuff, but what's basically happening is that the Chromebook uses Discover to identify the port partner. Then the Discover SVID lets him identify additional vendor ID information. It comes back with a Google SVID. If he trusts that device ID, then he'll discover any alternate modes. Looking at basically the response coming back. Okay, the power brick only supports one mode, which is what you'd expect from a wall wart, right? The laptop sends, please enter alt mode 1. Just like with power negotiation, he uses the object position to pick which mode he really wants him to enter. Then there's some additional proprietary messages sent by the Google Chromebook. Not clear what these are doing, but then the Chromebook issues a new request. He wants to renegotiate for more power. So he knows what the brick can provide now. He requests object 3, which is 3 amps at 20 volts. And that's it. So the CC line goes quiet after this, and it's done. So the behavior you see in this screenshot is it's very consistent when attaching the power brick to the Chromebook. Always goes through the same sequence. You may see some differences if maybe there's a low battery situation or some other variable, but it's very consistently the same when you're powering up these two devices. Okay, just a couple of tips on testing this new power delivery protocol. We used our flagship Voyager system, the M310C, to capture all of this PD traffic. It does support 10 gig Gen 2 super speed USB and power delivery. It has native Type-C connectors on it that allow you to sit in the line and capture these exchanges. A couple of interesting points to be aware of when trying to test with Type-C. Avoid using two marked cables in the analyzer. When you have a marked cable, the DFP can send cable messages, right, which actually pass through the analyzer to the other side. The cable doesn't eat the messages. So these SOP prime packets will actually pass all the way through to the UFP, and he's just supposed to ignore it. But both cables will receive the same message and respond. So you can have collisions or even contradicting responses as both cables reply to the same command. This could confuse the system because, well, there's not supposed to be two marked cables in the link. In most cases, you can just replace one side with an unmarked cable. It's pretty rare, but we've seen cases where one link partner won't come up because he doesn't see the RA terminations. So that may change the behavior of your system. And so we actually created a custom cable that has RA terminations but no E-marker. So you would put that on port 2, and basically you're spoofing the system. You're spoofing the device on the second port. Again, it's a cable that we make available, and you could certainly contact LaCroix if you're interested in that. Okay, so the USB-IF is finalizing the compliance spec for PD. We are active with that group and are actually working on supporting the full PD compliance plan. They found some vendors actually have configured their devices when they come to these workshops with only a single PDO, like 1.5 volts at, or 1.5 amps at 5 volts. So then basically the testers can't run a bunch of tests that are designed to verify that he can switch between different voltages properly. So they're ducking a bunch of tests. So going forward, it's going to be required that full PD silicon must support at least 2 PDOs. Okay. Also, beacon is an optional feature in USB, so don't over-rely on it. It's possible it might not be there on some hosts. Role swaps. Be sure and test under every condition possible. This was another area where we found a lot of problems during the workshops.